It is my pleasure to introduce the last speaker of this session and the last speaker of this year's GPCE conference, Matteo, who's going to tell us about automatically generated supernodes for AST interpreters.
Thank you for the introduction. Yes, this is a joint work done in collaboration with Daniele Bonetta from Oracle Labs and Walter Binder from Università della Svizzera Italiana, Switzerland. As the title suggests, today we'll talk about abstract syntax trees. Abstract syntax trees, AST for short, represent an elegant and straightforward way to implement programming languages. However, object-oriented implementation of AST interpreters often suffer from two main performance issues. First, many polymorphic call sites in the interpreter slow down performance. Second, these kind of interpreters usually make use of runtime exception to model the control flow on the interpreted language. Most of the research has focused on development and optimization of just-in-time compilers that transforms ASTs into optimized machine code. In particular, just-in-time compilation aimed at high steady-state performance. Unfortunately, poor warm-up performance remains an open problem for AST interpreters. For this reason, there's the need for new techniques that improve both interpreter and steady-state performance. I would like to list here the contributions of our work. In our work, we propose a new technique to improve virtual machine performance by exploiting AST supernodes, also known as superoperators in the context of bytecode interpreters. In particular, AST supernodes are compound AST node classes that encode the behavior of several other primitive AST nodes. Our technique automatically generates ahead-of-time supernodes and leverages runtime installation of matching supernodes. We implement our technique in GraalVM JavaScript engine, also known as GraalJS, and we evaluate our implementation on the web tooling benchmark suite. Experimental results show that our supernodes improve interpreter performance as well as steady-state performance. Moreover, our supernodes reduce the pressure on the JIT compiler, hence reducing JIT compilation time. I would like to present here the required background before describing our technique. We'll start with AST interpreters. An abstract syntax tree is a tree representation of a program where each AST node represents a language operation. In particular, we can divide AST nodes into control flow nodes if they encode the control flow structures of the language to be interpreted, such as if statements or loops, and non-control flow nodes that encode primitive operations, such as arithmetic operations. In an object-oriented implementation, AST nodes are often subclasses of a common abstract class. In particular, each AST node implements the code to perform the behavior of the operation the node encodes. Moreover, each AST node references its children and is responsible for their execution. This composition leads to many polymorphic call sites in the interpreter. That's actually one of the performance issues. The control flow of the language to be interpreted is usually implemented using the control flow structures of the language used to implement the interpreter. However, when this is not possible, for example, to implement break, continue, and return statements that span multiple AST nodes, AST interpreters often employ runtime exceptions. In particular, one AST node throws a runtime exception of a specific type, and another AST node, that is an ancestor of the first one, catches and handles the runtime exception. We would like to note that control flow nodes are usually found in the lower three levels of an AST, that is, closer to the root, while non-control flow nodes are usually found in the higher three levels, meaning closer to the leaves. As we mentioned, we implemented our technique in GraalJS, an open-source, high-performance implementation of JavaScript programming language built on top of GraalVM. GraalVM is a managed language runtime system that is based on a JVM, Java Virtual Machine, and exploits the Graal compiler. GraalJS is in turn implementing using the Truffle language implementation framework that allows one to implement self-optimizing AST interpreters running on GraalVM. Internally, the Graal compiler partially evaluates and JIT compiles ASTs. The AST node classes in GraalJS are subclasses of the abstract class node provided by the Truffle API. Each node class implements an execute method and declares the children the node accepts. To model the control flow, GraalJS exploits runtime exceptions. Since deciding what nodes to aggregate in a supernode is a non-trivial task, I would like to explain our techniques by providing a motivating example. In particular, we'll show an example how an example AST is transforming into one with one of our supernodes. We use as an example a JavaScript implementation on function Fibonacci, shown on the left-hand side of this slide. On the right-hand side of this slide, instead, you can see the corresponding AST. The AST contains many control flow nodes, such as function, if, return, and return exceptions, that throws an exception to return a value. The nodes represented with dash borders are actually compressed subtrees for the sake of visualization. I would like to briefly describe here the execute methods of the main control flow nodes. In particular, the one of function, if, return, and return exception nodes. The function node simply iterates over the children, calling their execute method. The function node then returns the value returned by the execute method of the last child. As you can see, there is no way for the adult children to return a value from the function. The only way to return this value is to throw and return an exception. In this case, the function node will catch the exception and return the value it encapsulates. The if node is implemented using an if-else statement. In particular, the if node evaluates the condition and then potentially executes the then or else part. In this case, the if has no else part. The return exception node indeed returns a value by throwing a new return exception. This exception encapsulates the value returned by the execution of the child. The return node instead, which is the last child of the function node, can simply return the value provided by the execution of the last child. In our technique, this AST is actually transformed into a corresponding AST with one control flow supernode. This control flow supernode avoids the usage of exceptions. Moreover, this supernode replaces the following nodes: function, if, return exception, and return. In this slide, you can find the implementation of the execute method of the control flow supernode. The control flow supernode simply executes the condition and then the then part of the fall through edge, that are the n parameter node and the recursive calls, respectively. I would like to describe now our technique. This diagram depicts the process of the VM building a workload execution. In particular, the white boxes represent the step required to build and execute a workload using a startup VM, while the gray boxes represent the additional steps required to implement our technique. When using a startup VM, one will need to build the VM at build time. Then, at execution time, the VM will need to be initialized. We can then proceed with source code parsing and then the AST creation. Finally, we can start interpretation. Later on, when the code has been JIT compiled, with the execution of the emitted code by the JIT compiler. Our technique introduces 3 steps that are namely the supercode generation that takes place at build time, the lookup tree generation, and the supernode installation, taking place at execution time instead. I would like to describe now one of each of these steps in detail. The first step is the supernode generation step. This step takes as input a collection of functions that we call the generation set, and produces as output a supernode, that is a Java class, for the lower 3 levels of each AST produced from the generation set. In practice, the supernode generation is implemented using an eager recursive algorithm. The algorithm is eager in the sense that the algorithm creates the maximal control flow supernode for each AST. At the moment, we do not deal with non-control flow supernodes, non-control flow nodes. This is part of our feature work. The algorithm recursively traverses the input ASTs. When a control flow node is encountered, the algorithm emits the code corresponding to the control flow node in the execute method of the supernode and traverses the node children. For example, the traversal of a return node first traverses the child node, and hence the node that produces the return value. Then it emits a Java return statement. When a non-control flow node is encountered instead, the algorithm creates an instance field in the super node to store basically the reference to the child node. To avoid polymorphic call sites, the declared type of this field is equal to the dynamic type of the child. Other than emitting the source code of the supernode generation step also associates a sequence of unique IDs to each supernode. We call this sequence of unique IDs the supernode structure. The supernode structure is useful to identify the subtree each supernode encodes. This sequence is composed of the type IDs of the encapsulated AST control flow nodes, as well as the type IDs of the children nodes accepted by the supernode. The second step of our technique is the lookup tree generation. The lookup tree generation takes as input the supernodes generated by the previous step, the supernode generation step, and returns as output the root of the generated lookup tree. The lookup tree is a prefix tree that efficiently maps structures to input supernodes. In practice, the alphabet of this prefix tree is the set of node IDs that occurs in the supernode structures. Apart from the root, each lookup node tree contains the type ID of an AST node and potentially a reference to a supernode. The lookup tree generation step is implemented using an iterative algorithm. Our algorithm creates the lookup tree nodes and edges by iterating over all the supernode structures. For each supernode structure, the algorithm iterates over all the unique IDs that compose the structure. Hence, for each supernode structure, the algorithm creates a path in the prefix tree and then associates the supernode corresponding to the structure to the last lookup tree node in the path. Consider the AST of function Fibonacci. On the right-hand side of the slide, you can find the prefix tree. The control flow supernode for the AST of function Fibonacci is encoded in the prefix tree with the path that starts from the root and ends with the add node on the left side. We'll show how our algorithm creates this path in the prefix tree. In this presentation, I'll traverse the AST. We notice that our algorithm traverses the unique IDs instead. First, the algorithm traverses the function node, hence the type ID of the function node, and creates the root of the prefix tree, which is empty. Then our algorithm traverses the if node and creates a node in the prefix tree, which is the if node there. Then our algorithm connects these two nodes with an edge. As our algorithm continues traversing the AST, we create the last-end node, the return exception node, the parameter node, the return node, and finally the add node. At this point, the algorithm associates the control flow supernode to this add node in the prefix tree. The last step of our technique is the supernode installation step. This step takes as input the program ASTs and the lookup tree, and produces as output the program ASTs with installed supernodes. The supernode installation is implemented using a recursive algorithm. This algorithm matches AST subtrees by traversing both each AST and the lookup tree at the same time. Then the algorithm instantiates the supernode corresponding to the matching structures, that are the supernodes that are stored in the last visited lookup tree nodes. Finally, the algorithm replaces the AST subtrees with the created supernode instances. Similar to the supernode generation algorithm, our supernode installation algorithm recursively traverses each input AST, as we mentioned in the previous slide. When a control flow node is encountered, our algorithm advances the search in the lookup tree by using the type ID of the visited node, which is a control flow node, and traverses then its children. When a non-control flow node is encountered instead, other than advancing the search in the lookup tree by using the type ID of the visited node, our algorithm collects the non-control flow node instance such that a supernode may reference this instance as a child. At the end of the AST traversal, the resulting lookup tree node potentially contains the matching supernode. I would like to present here an evaluation of our technique. In particular, we evaluate interpreter, steady state, and compilation time speedups. We conduct our experiments on GraalJS version 22.3.0 Community Edition based on OpenJDK 11 using the Graal JIT compiler. We modify both GraalJS and Graal to implement our technique. We perform our experiments using the well-known web tooling benchmark suite. And as a generation set, we use a collection of popular JavaScript packages. In our plots, we report on the x-axis the benchmarks of the web tooling benchmark suite, plus the geometric mean. On the y-axis, we report the speedup factors, computed as the execution time of a standard VM over the execution time obtained when using our modified VM. In particular, in this slide, we evaluate interpreter performance by disabling JIT compilation. In this case, we can see that our supernodes are effective, with speedup factors up to 1.55, 1.24 on average. This is because our supernodes reduce the size of the ASTs, hence the interpreter has fewer nodes to traverse. Moreover, they reduce the overhead of using expensive exceptions, as well as the number of polymorphic call sites. We investigate now the impact of our supernodes on JIT compilation, hence on the steady state performance. In this case, we perform our experiments without disabling the JIT compilation. Also in this case, we can see that our supernodes are effective, with speedup factors that range from 101 to 1.36, 1.14 on average. Finally, we evaluate the impact of our technique on the compilation time. In this case, we see speedup factors that range from 0.62 to 2.86. We can see a slowdown only on two benchmarks. We have a speedup factor of 1.33 on average. In this case, we can say that our supernodes reduce the pressure on the partial evaluator and the JIT compiler. This is because the partial evaluator has fewer nodes to evaluate, and the JIT compiler has fewer exceptions and polymorphic call sites to optimize. Before concluding, I would like to list here the limitations of our technique. First, the lookup tree generation and supernode installation steps increase the VM startup time. We are currently investigating techniques to serialize the lookup tree. Second, our supernodes increase the size of the interpreter. We would like to notice that, however, at runtime we measure a reduction in the size of the code emitted by the JIT compiler. Finally, the effectiveness of our supernodes depend on the quality of the generation set. In particular, a generation set will need to include functions exercising frequent control flow patterns. To conclude, we proposed a novel technique to generate AST supernodes. Our technique reduces overheads related to polymorphic call sites and control flow related exception handling. Our technique leverages ahead-of-time supernode generation and runtime installation of matching supernodes. We implemented our technique in the Graal VM JavaScript language runtime, also known as GraalJS. We evaluated our implementation using the well-known web tooling benchmark suite. Our experimental results show that our supernodes help reduce compilation time and improve both interpreter and steady state performance by factor 1.33, 1.24, and 1.14, respectively. As part of our future work, we plan to extend our technique to create supernodes that encode also non-control flow nodes. I would like to thank you for your attention, and I would be glad to answer your questions.
Questions?
Thank you for your talk. I do have a lot of questions. First of all, how do you come to think of doing it kind of top-down? So we have done something very similar in the past, but really focused bottom-up on the thing that you basically said is your future work. So what gave you the idea to do it top-down?
Yes. We started investigating supernodes with the idea of understanding what are the most common supernodes that we can create. It's actually an hard task to identify what they are unless you do a complex study in the wild. So we started by developing our algorithm to create eager control flow nodes that encode the control flow, which is what we presented today, and to see whether what was the speed up in that case. We decided to not optimize non-control flow nodes because they have we will need to extend the existing technique to do that. So we started by implementing the very the simplest thing we can do. So generate control nodes automatically in this way, see the speed ups, and only after maybe do a study in the wild to identify the most used ones. So yeah, we started investigating in this sense.
Cool, very cool. So how specific are these control flow nodes? So if you look at the various methods across different benchmarks and things, how applicable is the specific instance of a supernode across different benchmarks? So is it like there is one case per supernode where it's applied, or is it that it applies in many different places?
Yes. So we will actually need to perform a study for that. We tried to generate supernodes using different generation sets, meaning different libraries at the same time, and we see that we generate many supernodes for the first library. We generate some other supernodes for the second. As we go on, the number of supernodes we create in the generation step is it's getting smaller. So I guess there are control flow patterns that are frequently exercised by JavaScript developers. So kind of maybe kind of best practices that they implement. So there are definitely some supernodes that are widely used, while some others are not that used in this sense. We will need to perform an actual in-depth study to identify the best supernode in this sense. But this is what we noticed when developing our technique.
Thank you very much.
Thank you.
Hi, thank you for the very interesting presentation. I'm wondering how easily you think you could extend your work to other runtime platforms, and how specific what you've done is tailored to this specific VM and so on.
Okay. So I think that our technique can be actually applied to other platforms. We do have some specific parts in our implementation that are related to VM, but the general supernode generation algorithm, as well as the lookup tree generation and lookup and the supernode installation, is general. In our paper, you can also find the algorithms that are general. So in principle, we can apply this to other platforms. For sure, we can apply it to other truffle languages without without a huge implementation effort, since we have done it already for GraalJS. We believe that other VMs can adopt our technique as well, in this sense.
And if I can follow up with more of a, let's say, open-ended question, is how would you tackle, say, this kind of optimizations, but for VMs that have a completely different operational model? So I'm thinking things that aren't procedural like this. And for example, in the Prolog virtual machines, there's no control flow nodes like this. The operation is completely different, and there's no completely direct procedural approach. What do you think about these different paradigms, and could you go and attack these other virtual machines, which are similar but different in fundamental ways?
That's a good question. We will need to. I will literally need to think about how to extend our approach. At the moment, we have presented how to create supernodes for control flow nodes that are the most simple nodes that you can aggregate. Also, in GraalJS, for instance, we may need to deal with other more complex mechanisms. We're creating supernodes. This is an ongoing work. For example, to create supernodes, we are considering creating supernodes for nodes that have state machine internally. That they use a state machine to specialize over the types of their inputs, for example. So we are actually thinking at the moment how to extend our technique to support other other features or other designs in this sense. So I would say it's ongoing work. We are currently thinking about that.
Okay, thank you.
Thank you. I have one question about this non-control flow supernode, right? So you kind of suggest that it's actually more difficult for non-control flow comparing to control flow, which is kind of counterintuitive to me. Can you explain why?
Yes. Consider, for example, a primitive add node. So let's take Let's consider, for example, the add node. Here we are summing up the two values coming from the two recursive calls. So the add node the instance of this add node would, in GraalJS at least, specialize for the sum of two integers, for example. So primitive nodes in this sense, like the add node, internally have a state machine based on the types of the inputs. So this is what allows later the compiler to specialize the AST and efficiently compile it down to machine code. So if we deal with primitive nodes that may have to deal with different types, we need to create supernodes so we need to create supernodes. Probably these supernodes need to be bound to certain types because we don't want boxing when we execute code, the Java code. So we want a supernode to be specialized for certain types in this sense. Introducing supernodes that encode these nodes it's a little bit difficult since in the prefix tree you may need, for example, to add the types in a way.
Okay, one last short question.
But just imagine, I understand what you're saying about unboxing, right? But just imagine you have just a sequence of this non-control flow nodes, right? Why isn't it enough to simply merge them, assuming that this has already passed the type check and whatnot? Why do you still need to deal with the types? If you just have a sequence of non-control flow nodes.
Function Fibonacci here accepts an input n. We don't have actually the full vision of the entire program because there may be dynamically linked code and so on. So one user may actually pass to Fibonacci a string. In this case, JavaScript will just sum the string with some numbers in a sense. So we don't have the type checker that says, okay, here the input is always this input and so on. So we need to preserve the behavior of the VM, and we need to deal with several different types. And we cannot assume that this function always takes an integer, for example. So.
Okay, let's thank Matteo again.
Thank you.